video today, B.4, general solution of fake coin problem. All right. Now, we need to consider the, more general case, more general. So we do step by step. Yeah. Because it is not easy to jump from n equals 3 to the general case. Yeah. All right. For the general, so we like to consider a case relatively easier for us. Okay, relatively easier for us. Okay, yeah. So that is, we consider n is a multiple of 3k. Because in this case, we can use the balancing principle to make a perfectly distributed arrangement. 3 different states, each one we can allocate k coins. Yeah. So 3 piles, each one has k coins. So that's the most balanced arrangement. Yeah. So let me using this way to represent. Okay? Yeah. So pile 1, number of coins, k. Pile 2, also k. And pile 3. Yeah. So in this way, we use the similar weighing method as the n equals 3. Yeah. But this time, we place pile 1, pile 2 on the balance scale. And similarly, 3 cases. The middle case, even fake, is in pile 3. Okay? First one, pile 1 lighter, so we can say fake is in pile 1. Yeah. Third case, fake is in pile 2. Yeah. Now, from this analysis, we can make conclusion like this. After one weighing, the size reduction is like this. Okay. From original size n to k, we reduce the size from n to k, or 3k to k, divided by 3. Okay, yeah. So that's a special case. Yeah. So we want to know how to handle the case that n is not multiple of 3. Yeah. So we need to make n as the general possibility. Yeah. Yeah. So let's go to the next case. So this time, when we consider size reduction, we assume n has the form 3k plus 1. If we use 3, yeah, so n divided by 3, the remainder is 1. Yeah. And that is another special case. All right, but this time, we use the balancing principle, try to distribute 3k plus 1 coins as even as possible, not perfectly evenly distributed, but the best we can do, pile 3 contains k plus 1 coins. The remaining 2 piles, k coins each. Yeah, so that's the best we can do. For this situation, we can still use one weighing to determine the fake is in one of the 3 piles. Yeah. All right, so because pile 1, pile 2, they have the same number of coins. So the most reasonable way to choose the piles is like this. Yeah. Still, 3 cases. The middle one, pile 3 has the fake. top one, pile 1 has the fake. Bottom one, pile 2 has the fake. Okay? Now the conclusion. Conclusion for this one, the size reduction becomes from n to k plus 1. Although 3 cases, the other 2, the fake is in a pile containing k coins, but this one, k plus 1 coins, worse than the other 2 cases, right? Worse. And we want to look at the worst case. Yeah. If we can handle the worst case, then the remaining other cases, we can only do better. Yeah. If we take care of the worst case, for the remaining other cases, we can only do better than the worst case. Yeah. So that's why we want to make this conclusion. Size reduction from n to k plus 1. Size reduction. Okay? Yeah. Similarly, we consider the remaining, the last 2 cases. Yeah, because when n is an integer, n only has one of the 3 cases. 3k, 3k plus 1, 3k plus 2, right? So that's the only 3 cases we have for n, integer n. Yeah. So the last case, we need to consider this one. In this situation, by the balancing principle, we do this kind of coin allocations. Okay? Then the worst case, we should put pile 2, pile 3 on the scales, right? Yeah. The worst case should be in one of the piles containing k plus 1 coins. Yeah. So the reduction, so this time reduction, size reduction, still k plus 1. Right? Yeah. Now, we want to use one formula to represent the size reduction. Yeah, because here we have 3 different cases. The size reduction ways are different. Can we use a unified way to represent the size reduction for the general case? Yes, we have one formula. Okay, the formula is like this. Size reduction from n to ceiling function of n over 3. Okay, so you can see, you can check. This case is correct. Ceiling function. Rounded up. Okay, this case also correct. Rounded up. Okay. And n equals multiple of 3 also correct. Yeah. So this is one unified representation to cover all the cases. All right, yeah. Next, now, because we need to solve the problem. We haven't solved the problem. We make some good progress, but we have quite some work to do. Yeah. So the next, we need to try to reach the goal of this problem. So what's that? How to represent the minimum number of weighings in terms of n. That's how we translate the original question to this version. Minimum number of weighings in terms of n. Yeah. Okay? Yeah. All right. When we look at this formula, what is the simplest case? This one is the size reduction formula. But using this formula to get an answer, we want to consider the simplest case first. That's the strategy we used many, many times. Here we need to use it another time. Okay? When we look at the seeding function, so you can see if n is not a multiple of 3, it is not very convenient. We have the rounded up operation, not very convenient. Okay? Yeah. But when we work on general n, we need to do size reduction many times. So many times reduction in this way. What is the best case you can imagine in this situation? So that is when the size is a power of 3. Then every time you divide by 3, no remainder. You can do the perfect division, right? So that's the easiest case. We can work first. Yeah. So we assume n equals 3 to the kth. All right, so now when we do that, here I want to do a chart to find the answer. Yeah, because that will be, visually easily understood. Yeah. All right. At the beginning, when we have no weighing, yes, here, this column, the number of weighings we do on the coins, data size, okay? Yeah. Before we do any weighing on the coins, the data size 3 to the kth. Next, we do the first weighing, then we reduce the size divided by 3, right? So 3 to the k minus 1. Another weighing, we reduce the size by another division by 3 operation. 3 to the k minus 2 power, okay? And so on. So we'll keep going like this way. At the end, what do we get? Now, here we have the situation, it may not be that easy to keep track of the change, right? Yeah, because in this ... how do we keep track of them, right? We skip many of the cases. Can we find a rule? Okay, yeah, because we cannot exhaust all the possibilities, right? Impossible. So we need to find a rule. When we find a rule, here I want to use a method I introduced a long time ago. I hope you still remember. Some of you still remember that method. Invariant method. When we need to keep track of some, data relationship, okay? Yeah. In that situation, if you can discover some special invariant quantity, then it helps us to figure out the relationship, the data relationship. So here, look at this. Exponent k plus 0, what is that? K plus 0, that is k, right? Yeah. Exponent k minus 1 plus 1, what is that? Also k, right? Exponent k minus 2 plus this 2, what is that? Also k. Can we say the invariant is k? Yeah. For any row, you have this invariant quantity. Okay? Yeah. So based on this observation, we can get invariant E plus W, E exponent. Okay? The left column exponent, W right column number. Okay? Yeah. That number equals K. That's the invariant. With this property, now we can look at the bottom 2 rows. Because this one, we know the data size equals 3 to the first. Based on this relationship, k minus 1. After k minus weighings, we reduce the problem size to this one. Okay? Last row, the destination, 3 to the zeros, 1 coin left. That's the fake. Yeah, because we narrow down, finally we reach only 1 coin that contains fake. That's the answer. When E equals 0, W equals K. 0 plus K equals K. Yeah. So this is the answer. So we find the answer. Yeah. All right, so this is the answer. Yeah. But we need to write it in terms of n. So log base 3 of n. Okay? From here, log base 3 of n. So for this special case, we find the answer. Okay. All right. So next, how to find the minimum number of weighings for the worst case. Okay, yeah. All right. For the worst case. Yeah. So here, what I mean, for the worst case, for the general n. Okay, so not that. So here we need to consider the general n for this question. Okay, can you guess answer? Because here we have this one. For the general n, this expression may not be integer, right? Yep. Log base 3 of general n, positive integer, this whole expression not necessary an integer expression. But our number of weighings must be an integer. How do you convert it to an integer expression? Floor function or ceiling function. We have 2 ways to make it integer representations. Rounded down or rounded up. So floor functions or ceiling function. But which one is correct? So here the question is, which one is correct? So we need to find the answer. Yeah. So our last slide, we need to find this answer. Our final slide of this video. Yeah. Not very hard, so we can figure out. Yeah. Final solution for a general n. How do we know the minimum number of weighings is representation in terms of n? We're almost there, but we have a critical step we need to do. So what's that? For a general n, positive, yeah, definitely greater than 2, right? Yeah, given condition. Yeah. We can find k such that n is between power of 3 to the kth power, less than or equal to, and strictly less than 3 to the k plus 1th power. Can we do that? Yes, we can do that, right? Yeah, we can find that. Yeah, it's possible, right? Yeah, so the k number is between these 3 numbers. All right, now we apply our power of 3 solution we derived in the previous slide. We applied here. Okay? For this many coins, how many weighings for the minimum number of weighings for the worst case? How many? Yeah, we derive it, k weighings. Yeah. For this case, how many weighings? This many coins, k plus 1 weighings. Now we get back to n. What is that? All right. So here you can assume, yeah, because the equal case, then you get this answer, right? So here, how about we consider strictly less than n case? Yeah, because this number between these 2, so the answer is either k or k plus 1, right? Should not be greater than k plus 1, right? Yeah. So one of these 2 numbers. but n greater than this one. So it may not be possible to use k-weighings to solve this problem. So based on that, we guess it's very likely it should be the ceiling function. More likely to be the ceiling function, not the floor function. Because the floor function, that means you get this number of weighings, but you have more coins than power of 3. Is that possible? Right? Yeah. So, all right. So based on our intuition, we think this is the answer. This is the answer. But we need one more step. Yeah. For things like this, we can make the guess. We can make the reasonable guess. But to get a final solution, in order to convince people, can you make the final convincing argument? Okay. So here we need a final convincing argument. Right? Final convincing argument. Yeah. All right. So here, I leave it as an exercise question, so you can think about it. Yeah. But here, I want to let you know my next class video, I plan to do a problem section. Yeah. So there is the reason. Yeah. Here, let me. In my original plan, I did not plan to do problem session, but now I feel I need to do it. There are some reasons. First, I noticed many students cannot keep up with the pace of the, current our videos. Yeah. Because many videos, the watching rate very low. Yeah. So many students have not watched the videos. So I feel I need to slow down a little bit. So our next class, I do not give you the new material. But I feel another thing also important, problem solving, right? So I want to give you a few more examples. Yeah, because I will assign you homework number 1 soon. Yeah, tomorrow I will give you homework assignment 1. Yeah, so after assign that, then I will use one class session to explain some of the questions. Yeah. Some of the questions in our quizzes I can select. So I feel I need to explain a little bit. And I also pick some of the questions, related to the homework or related to, something like this. If I need, I can explain. So in the lectures, there are some questions left. I can also explain if I have time. Okay. All right. So on Thursday's class, I will do a problem session. Yeah. All right. Yeah. So we finish part B now.